we're going to finish chapter 3 today, and then next week we'll have a review for the first exam. And what I usually do is I take those homework questions and run through some of those. But I may also have another document that will have some example problems in it, and that will help give you topics that you can expect covered on the exam. All right. So we're going to talk about atomic structure and the periodic table today. That reminds me that the periodic table that I gave you with the red boxes on it to which ones to memorize, do you have a copy of that with you? I found an error in there, and I want to correct that before we go any further. Yeah, I see it. That's got the error in it. Look in the upper right hand, helium. See, helium's got a blue box on it. That's a major error. Helium is not diatomic. That's what that blue box means. Those gases are diatomic that have blue boxes on them, and helium is not supposed to be one of them. Helium is a noble gas. It's not going to bond with anybody, much less its own kin. See it? I see it. Yeah. Be sure, don't consider helium diatomic. It's not. I'm pretty sure I corrected that in Blackboard. So if you want a fresh copy, go to Blackboard and you'll find the know these periodic table. And it should have a corrected form in it. Okay, that's out of the way. Let's get to the topics here. Yep. Okay. Now we're in business. Okay. I've always got an outline at the beginning, but we don't need to stop there. How do we remember we covered Dalton's atomic theory, correct? Have we done that? It didn't ring a bell. Okay. Well, in case we hadn't, I'll tell you what, let me look to see. I may be stealing my own thunder. I don't see it in here. So we must have covered it. Well, Dalton's atomic theory just simply referred to elements in terms of the smallest particle that still retains the identity of the element, and that's the atom. But Dalton's concept of the atom was kind of like a billiard ball. It was just a thing. Couldn't divide it any further. I mean, that's what atom means. You can't cut it anymore. So when he proposed his theory, he didn't know about subatomic particles. He didn't know how atoms were built, but we do know that now. He did assume that each element and the particle, the atom, was different for each element. Okay, so ancient Greeks didn't come up with that. They thought that all matter was composed of the same atom, and that got them into a lot of trouble. They couldn't explain some things. But when Dalton said that the elements are made up of different atoms for each element, that solved a lot of problems. Only he didn't know why they were different. Now we do know why. And it's all based upon subatomic particles. We do know now that an atom has at least one electron and one proton. Most of them have more than that. And most of them have neutrons. The only one that doesn't have a neutron is hydrogen. Okay. In fact, there are a couple of, we'll talk about isotopes in a minute, but there are a couple of isotopes of hydrogen that also have neutrons. So there's only one isotope of hydrogen that has no neutrons, and the rest of them all have some neutrons. Well, what's the difference, right? Well, protons are positively charged. Electrons are negatively charged. So they cancel one another out in a neutral atom. There'll be the same number of each one, because the charge for an electron is equal to the charge of a proton. So if you have one of each, you got a neutral atom. Or if you have two of each, you got neutral, as long as they're equal numbers. But the proton doesn't account for all the mass of the atom. Well, it was very apparent when scientists were beginning to tease out the structure of the atom. They learned that, well, okay, we're sure there are protons in there, we're sure there are electrons in there, but that doesn't account for all the mass. So it has to be something else in there. And that's the neutron. And they knew it couldn't have a charge, because if it had a charge, then this whole scenario was blown up. So it had to be neutral. So we know now that the protons and the neutrons occupy a very dense center to the atom, called the nucleus. That's where most of the mass is located. But most of the volume is taken up by electrons, right out here in this cloud around the nucleus. Now, the relationship mentioned before between the charges is, we'll move on from that. The masses, however, the protons and the neutrons are virtually equal in mass. They're not exactly equal, but they're pretty close. But the electron is 3.5 orders of magnitude less massive than either the proton or the neutron. The ratio is about 1,800 times smaller in mass for the electron. Oh, there it is right there. It's a read my own chart, right? So the proton is this much heavier than the electron, and the neutron is a little bit heavier. That makes sense if we had time to talk about the nuclear decay, but we don't. So we'll move on. They're almost the same. All right, mentioned this already. That's where the protons and neutrons live, in the nucleus. And as long as you've got the same number of protons and the same number of electrons, then you have a neutral atom. So what do we call an atom that has different numbers? Call it an ion. So just to review, subatomic particles of an atom are these three. Those are the main ones. I mean, if you really get into this stuff, if you make a career of it, there are subatomic particles. But that won't do us any good in chemistry to study those. That's only for physics fanatics. Okay, so when we write the symbol for an atom, if we want to include information about the nucleus of that atom, then we write the symbol, and I'm going to use the generic X. There's no element up there with just an X. And there are 4 positions around here that are reserved for specific information. So down up here in the upper right-hand corner is charge. Okay, if it's charged, you'll have a plus, a minus, or 2 plus, 2 minus, 3 plus, 3 minus, whatever the case may be, will be in this position. If you have more than one atom, say in our diatomics, that number will be down here. Or if you're writing a compound and you need more than one atom in the compound, that's where you put the number. If we're talking about the nucleus of the atom, of that element, then down here goes the atomic number. And the atomic number in this chart, at least, is in the lower left-hand corner, these red numbers. That is equal to the number of protons. Okay. Originally, the atomic, yes.
Oh,
Okay. Originally, the atomic number had nothing to do with protons. A young chemist by the name of Moseley, an English chemist, was working with metals in particular, and he was firing X-rays at them, and he was measuring the wavelength of the light that emitted from the element after he bombarded them with X-rays. And he noticed that the wavelength of each element was different in a particular region. He was very specific. He selected one region, and the wavelength in that region for that emission for that element was unique for each element. And he devised a formula. We don't even know what it is, but there was a number in there that all he had to do was change that number, whole number, 1, 2, 3, 4, 5, whatever it happened to be, times whatever was in this formula, and then always give him the wavelength for each different element. And that number was different for each element. And we now associate those numbers with the number of protons. So Moseley came up with that mathematically first, and then we made the physical association between the two. Unfortunately, Moseley enlisted in the English Army for World War I, and he died in battle. He was a young fellow, and that's as far as he got in his career. Okay, and the other position here, let's see, we designate that A. This is the mass number. And it's the number of protons plus the number of neutrons. Okay. So we've got all those four, they've got those four positions reserved. In chemistry, when we're talking about elements and compounds in a reaction, we don't write that information in there. It's not necessary. But if you're describing particularly isotopes, where have different numbers of neutrons, then you do need that information. But for chemical reactions, we just fill in these parts right here. Another thing to remember, if it's not obvious to you already, this number of protons, if you know the number of protons, you can find the element. I mean, they're joined at the hip. Just look up the Z number, this atomic number, it's the number of protons, and it's always a different element. Okay, so if you know the symbol, you can find the number of protons. If you know the number of protons, you can find the symbol. Right there. They're twins. And that brings up the issue of ions, if I'm not skipping ahead too far. We're going to talk about ions. We just print it upside down. Okay, just in case, I'm going to talk about it right now. So if we can put a charge here of any kind, think about how you get that charge. And what I just said about protons, right? If you change the number of protons, you've changed the element. So if you want to make an ion of an element, don't touch the protons. Don't touch the positive charges. You make ions with electrons. Either more electrons makes a negative ion, fewer electrons makes a positive ion. It's the balance. So whatever this number of protons is, if you add electrons to that atom, it'll make it negative. You know, 1 electron will be a -1, 2 minus, 3 minus. Or if you take away electrons, you have an imbalance in favor of protons, and that makes a positive ion. And that's what most metals do. All these guys over here, from here all the way over like that, or down here. They like to lose electrons. Whereas the non-metals, and we haven't even talked about that. I'm getting ahead of myself. periodic table, unless you've done the periodic table and you know what I'm talking about in that extra credit. Okay. So this is animated fun for what I just talked about there. As an example, sodium always has 11 protons. And you can look up here and see there's sodium with 11. And the way the periodic table is arranged, from left to right and top to bottom, the atomic number gets bigger. So if you're trying to find something, just sweep from left to right and top to bottom until you find your number. Right? Just keep going until you find the right number. And there you found your element. Okay. Elements are considered pure substances. In other words, you cannot separate out, if you have an element, you cannot separate out anything else other than subatomic particles. And this is by physical means. So you can't get at the subatomics anyway. If it's pure, then there's no way to separate physically other substances from it. Now this goes for elements and it also goes for compounds, like water, for instance, is a compound of hydrogen and oxygen. Well, it's a pure substance because the only way you can get at the hydrogen and oxygen is by chemical means. Physical means will not separate those two. So it's considered a pure substance. Okay. And of course, all the atoms have the same atomic number. That should be obvious by now. And they have the same chemical identity. That is, they react the same way. And how do you know that? Well, you have to add them to other elements and see how they behave. Well, that's the chemical behavior. The physical behavior you can do without introducing other elements. For instance, metals are going to be malleable. You can shape them. They're ductile. You can stretch them into thin wires. They shine. It's called luster, especially if you polish them. They're good conductors of heat. They're good conductors of electricity. Those are metals. Whereas nonmetals, and most metals are also solid, except for which one, right? They're at room temperature. Mercury is a liquid. The rest of them are solids. But with nonmetals, I think I'm skipping ahead, but that's okay. This is a stream of consciousness. The nonmetals, which are over here, they can be either solid, liquid, or gas. You got some solids here. There's phosphorus and silicon. These guys right in here. Boron's a solid. Carbon's a solid. These are gases right here, gases. And that one. Bromine's a liquid. And iodine's a solid. Okay, so you have, for nonmetals, you have a mix of physical states. Plus, they're usually pretty dull in appearance. They don't shine. You can't stretch them. They're brittle. If it's a solid, it'll break before it deforms. But they're all pure substances. So the atomic number is the number of protons, and in a neutral atom, it's also the number of electrons. So that's your starting point, the neutral atom. If you need to make an ion, start there. Or if you're given an ion, you know what to go back to find out the identity. So I have for example, I tell you that this one has a 2+ charge. And I also tell you that there are 20 electrons. Find out what element that is. If it's got 20 electrons, but there are 2 more protons than electrons, how many protons does it have? 22, right? 22 protons. Now you can go to your periodic table and say, all right, 22 is titanium with a 2+ charge. Okay, that's the detective in me that works that problem. Okay, now we'll have an official discussion of isotopes. I've referred to isotopes before without defining them. But an isotope is simply an atom of an element that differs from other atoms of the element in the number of neutrons. So it has the same number of protons, that makes it like all the same element, but number of neutrons makes them different masses for each atom. So for instance, carbon, the most common isotope of carbon with 6 protons is mass number of 12. So how many neutrons do we have in that isotope? 6, right? Because this number is that one plus the number of neutrons. So subtract this from that and you get the number of neutrons. Okay, there's another isotope of carbon that has a mass number of 13. So we have 7 neutrons in that one. And then the one that gets a lot of publicity is carbon-14. That's stable. That's stable. This one's radioactive. It decays. It changes into another element, actually. And it has 8 neutrons. Now, as it turns out, the stability of isotopes relies entirely upon the number of neutrons. For the longest time, scientists couldn't figure out. I mean, we know the neutrons are there. It's been proven. Chadwick proved that in the early 20th century. He got a Nobel Prize for it, too. But we really didn't know what their purpose was. And eventually, it was confirmed that the purpose of the neutron is to stabilize the nucleus. Because think about it. If you got this dense body in the middle of your atom, and it's just packed full of positive charges, what's to prevent those positive charges from just flying apart? What keeps them there together, right? That's the purpose of the neutron. It's there to stabilize all those positive charges stuck in that small space. And as you get heavier and heavier, you need more and more and more neutrons, because the effect of the neutron is very short range. Right? So if you get a big nucleus, you need a whole lot more neutrons to stabilize it. So I won't say any more about that because it looks like your heads are about to explode anyway. Okay, these isotopes, while they have different numbers of neutrons, they have the same protons and the same number of electrons. So they behave, chemically they behave alike. Right? So they have the same chemical and physical properties, definitely chemical. Physical properties are slightly different because of the mass is different. But they behave similarly, chemical and physical. Most elements found in nature exist in multiple isotopes, just like carbon. In nature, actually, there are more isotopes than that. But these are the 2 stable isotopes, and the rest of them are radioactive. So even if you've got them in a sample, pretty soon they disappear. Or if you make them in the lab, they don't last very long. Now, that's not the case for all isotopes. Radioactivity runs the full gamut. Some isotopes will decay in milliseconds, and others will last for a billion years. So you've got a wide range. But these, for carbon, these are the 2 stable isotopes. And they exist in the naturally occurring elements exist in usually multiple isotopic forms. And that's why when you look at your chart and you see these numbers up here, in this case in the upper left-hand corner, those are atomic weights or molar masses. We'll talk about that a little more later. But you notice that they're all fractions. None of them are whole numbers. They're related to these values here, but they're weighted averages. Because if you have one isotope that's dominant, then that number is going to be closer to this one. Right? For carbon, this is the dominant form. But if you have these in here with a little bit heavier, then they're going to skew that average up a little higher than 12. See what I'm getting at? It's kind of like figuring your GPA average, right? Weighting the weighted average of your GPA, you want courses where you've taken 3 and 4 credit hours, you want those to be A's, B's. And then the ones that are only 1 credit hour, you can stand those to be C's. They will have a major impact on your average. It's a weighted average. We'll come back to that topic later. Okay, so here's an example of silicon. And it's in 2 of its isotopes. Right? This one has, they always have the same atomic number, because that's the number of protons. And then the mass number will be different because of the different number of neutrons. Okay. So there's the mass number and the number of neutrons differ. Okay. All right, a little detective work here. We've got an element that has 23 protons and 28 neutrons. So what's its mass number? You have that here, 51. So a mass number of 51. Okay, what's the element? Well, we know the number of protons. All we have to do is just look on the periodic table. There it is right there. It's vanadium. Okay. Now, when we're doing calculations in the lab, and say we have we determine experimentally that the molar mass, so the molar mass is some, I don't know, 51.32. You can still use that information to find out what element it is, even if you don't know the number of protons. Because most of these elements, as you increase their atomic number, you're also increasing their weights. So you just look along there and see which one comes closest to the weight, and it's still vanadium. There are only a couple of places in the periodic table where the weights are so close together that, you know, it's kind of a flip of a coin. But for most investigations, if you know the atomic weight, you can usually find the element too. All right. Oops. There it is, vanadium. All right, so here's more of the carbon story. I said carbon-12 was the major player in natural abundance. So it's almost 99% carbon-12. And then you have a little bit of carbon-13 and just almost no carbon-14. But there is enough carbon-14 in samples, fossilized living samples, used to be living, that you can determine their age simply by the decay rate of carbon-14. You've heard carbon dating. That's what it is. They just say, all right, if the ratio of this carbon-14 to carbon-12 is a certain value, when the animal or plant was living, then once they die, they stop taking in carbon. Right? So what the carbon they start with when they're dead is what gets fossilized. So at that point, it's a fixed ratio, and then this starts decaying. And you can measure how much is left over and ratio that to this one and make a statement about how old you think that fossil is. Now, there are limitations because and it's based upon the decay rate. Right? The decay rate of elements that take a long time to decay, which is known as their half-life. How long does it take to half of it to disappear? Once you know that, then you can decide, which radioactive isotope to choose to determine the age. So if you have rocks that you think are really, really old, you want to use a different isotope that has a longer half-life. Then you can go further back in time. For carbon-14, you probably can't go much farther than maybe 15,000 years, something like that. Anything older is there's not enough of it left. You can't figure that one out. Okay, so back to this topic. So the atomic mass, not the mass number, but the atomic mass is a weighted average of these values. So you would take, what would be the decimal equivalent of that percent? Just move the decimal to the left, right? 1, 2, be 0.989. That would be the decimal equivalent of percent. And you would multiply that times its value, and it'll give you a number. So that's its contribution to the atomic mass. And then you would do the same thing here, 0.0111 times 13, that would be a number. And then this is so insignificant, we won't even consider that. And then just add them together, and you get a value that's close to the one reported in the periodic table. Rounded off 2 decimal places is 12.01. Well, the problem is that we don't have a reference point. In our discussion so far, we haven't used a reference point because just because we say it's this doesn't mean it is. So we need something that scientists agree upon as a fixed position, and then everything else is referenced to that. So they chose carbon. Originally, they chose oxygen because oxygen was in everything. It's the most common element on the planet. Problem was getting a pure sample of oxygen for reference. Right? First of all, it's a gas. And second of all, it was difficult to obtain from that a pure isotope of oxygen that would be 16. So eventually they settled upon carbon. Carbon's a solid. It's easy to find, easy to purify, and they identified this isotope fairly easily. Since it's major abundance, it didn't take too much effort to remove that contaminant. So you would end up with carbon-12 isotope, pure. And that would be your reference. And they assigned that one to be exactly 12 atomic mass units. Okay, everything else is referenced to that. So you take that, you compare the mass of that isotope with any of the others, and that means that their atomic mass units are never going to be whole numbers. I know that I can see the confusion. Atomic mass and mass number are different. They're related, but they are different because the mass number can be calculated by the number of protons and number of neutrons. That's easy. It's always a whole number. But the atomic mass is referenced to this isotope. So that's the only one that is 12 point, however far you want to go. All the zeros you can write by definition. And then everything else is referenced to that, which means that all the other atomic mass units for other isotopes are going to be not whole numbers. It's just a fact. Okay. But for argument's sake, Let's assume for the second, well, of course, this one's going to be 12. This one's not going to be exactly 13, but let's just, for argument's sake, assume that it is. It won't be very far from that. And then if we're going to calculate the average atomic mass for naturally occurring carbon, we would do a weighted average. So this one would be this percentage of 12, which would be actually the decimal value times 12. Let's do that. So you've got one carbon with 12 atomic mass units times 0.989. 9889. There we go. So what's that value? Let's get out the calculator. All right. So 0.989 times 12. All right. I didn't already do that, did I? No. We didn't do it that detailed. All right, so that's going to be 11.8668. 11.8668. Atomic mass units. We haven't defined atomic mass units yet, but hold still, we will. So then this isotope would be what fraction? 0.111. So 13 times 0.0111 is only 0.1443. So if you add, this is the contribution from that isotope, this is the contribution from that isotope, and then we just there, atomic mass units for naturally occurring carbon, taking into account the relative abundance of each isotope. 12.01 rounded off to 2 decimal places. That's where those values come from. They'll change over time as our instrumentation becomes more precise, accurate. Then they'll reevaluate the elements and post an updated periodic table through the official channels. And usually the variation occurs in about the 4th, 5th, 6th, or 7th decimal point. So it doesn't affect us at all. We can use a periodic table that's 30 years old. It's perfectly all right. Okay, any questions so far? All right. Oh, this is a good one. Say we have an element that's identified and consists of 62.6% of an isotope that has a mass of 186 atomic mass units, and 37.4% of 184.953 atomic mass units. So they're actually using the atomic mass units that are referenced to that carbon standard. Right? Notice they're not whole numbers. So if we run the numbers and we say 0.626 times 186.956, that equals a value, and then 0.3740 times 184.953. That's a value, and then we add those two together. Then we'll get an average atomic mass. Right. So rather than take up the time to do that, I've already got the answer here. So this should end up at 186.207 atomic mass units. One atomic mass unit is approximately the mass of a proton, in case you were wondering. So hydrogen should have the the most abundant isotope of hydrogen should have a mass of 1 atomic mass unit. Okay, so what element is that? Remember what I said about finding elements using the atomic mass? Well, we just look along here and say 186.207. I'm gonna have to get closer. I got old eyes. 186.207. Let's see. Well, look at that. 186.207. Rhenium. Now, is there anything else close? Right. On the other side, rhenium, 190 for osmium, and 183.85 for tungsten. That's W is tungsten. It's Latin, it's wolfram. Okay, so that's rhenium. All right. And it has 75 protons in it. So can we say anything about the number of neutrons? What about this isotope? What do you think the number of neutrons would be? Probably rounded off 187 would be the mass number. So 75 from 187 is 112 neutrons. What about this one? It's probably 185 is its mass number. So it would be 2 less, 110 neutrons. Okay. So you can make some intelligent guesses with this information too. Let's see. There it is. Rhenium. I didn't make you memorize that one. I didn't request that you memorize that. I can't make you do anything. Okay. Test the question, quiz time. Atoms of an element that contain a different number of neutrons, isotopes. Okay. Let's take a more detailed look at the periodic table, how it's organized. Actually, Dmitry Mendeleev was given credit for putting together the first useful periodic table. But there were attempts up to that point at making sense of the behavior of different elements. There were triads, they called them. So three groups or 3 elements that behave similarly, like the halogens, chlorine, bromine, and iodine. The chemists knew that they behave similarly when they reacted with other elements, particularly if you try to react them with one of these metals. That's a pretty violent exothermic reaction. Or they could group, let's see, well, the alkali metals, lithium, sodium, potassium, they behave similarly. Those are triads. Then along came Lothar Meyer, who was a German, and he tried to organize more of them together. And he published his version of a periodic table, but he never took it very far. He didn't use it to say anything about the elements that were discovered or about elements that may have been undiscovered. That's what Mendeleev did. Mendeleev organized the elements into groups. We used to call them families because they behave similarly. And he'd go along and he'd put these elements in this group, and then he'd have elements in this group. Say like this would be a group of elements in here. And then next door to them would be, this would have a, and he did it all by atomic weights. Right? They knew nothing of atomic numbers during Mendeleev's time. He was a Russian, which is neither here nor there. But they were organizing things by atomic weights. So he put this one, and the next door would be a heavier one, right? And then he put a heavier one here. Well, as he started getting groups together, right? Side by side, he'd get this one heavier, but this one would be the next heaviest one here, but it didn't fit in that group. Didn't have the same chemical and physical characteristics. So he said, it's more like this one. So I'm gonna move that one over here and leave a hole right here. He said, one of these days, somebody's going to discover an element to fit that place. And it's going to have approximately this weight and these characteristics. And he was right. They did find an element to fit those holes that he left open. That's why he's given credit for the periodic table, because he used this information to predict the existence of non-existent elements at that point. Okay. So we've got groups. Let's see. Vertical columns are the groups. Right? So each of these columns, these elements have similar behaviors, similar chemical and physical behaviors. Now, these first two columns and these last 6 columns are known as representative elements. All taken all together. And the grouping, the families tend to be well behaved. In other words, all the halogens behave a certain way, and all the alkaline metals behave a certain way, and all the alkaline earths behave a certain way. The chalcogens behave a certain way, the oxygen group. The nicogens behave a certain way. The carbon group, the boron group, they all behave a certain way. When you get into the transitions here, right, they're sort of similar, but for electronic reasons, internal to the atom, the element, the difference between them is not as great as it is from this group to that group to that group, that group. Okay. And the periodic table is arranged based upon the electronic structure, the energy levels of the electrons in that cloud outside the nucleus. Right? So if you know how the periodic table is structured, you can take that knowledge and the number of electrons, which would for cobalt would be 27, and you can put them in energy levels based upon the position here. You know where everything is supposed to be, and you can write the electronic structure from the periodic table. That's how it's organized. Okay, we talked about groups, similar behaviors. Now we've got periods. Oh, we're going to do a little history. Okay, hold on a second. We'll get to that in just a second. Groups are this way. Periods are left to right. Right, so when I think of periods, I think of periodic motion from physics. Periodic motion where an object moves through some distance in a cycle, it always comes back to the same place, like a pendulum. That would be periodic motion. There are lots of types of periodic motion, but that's the easiest one to comprehend. So think of this, if we're moving from left to right as things get heavier, okay, and then we get down here, and the next heaviest one, well, it looks like one of these. So you double back, you start over again. That's the period. You've gone through a whole cycle and you're back to the beginning again. That's why they call it a period. Okay, so the triads I was mentioning before were proposed by another German, Dobereiner, in the early 19th century. Then along came Lothar Meyer. And his concept was valency. Valency has to do with the way elements react. Now, at that time, they didn't understand fully what they were saying when they said valency. We know now valency means how many electrons in that outer cloud are available to interact with other elements. Those are the valence electrons. But he assigned valency to various elements And he organized them into a table about 1870. And about the same time, Mendeleev did a similar thing, only he used his to predict the existence of, like I said, undiscovered elements. And that's why he gets credit. And then I mentioned earlier Henry Moseley, who was the fellow that did that X-ray spectroscopy on metals and discovered the atomic number. He didn't associate it with protons at that time, of course, but eventually it did happen. Okay, so I mentioned groups and periods, explained what those were. Some of those groups have names, and I mentioned a few of them, and if you do the extra credit, you'll learn them. Alkali metals are the first group. Alkaline earths, these are transition elements here. This is the boron group. It doesn't have a special name. The carbon group. Pnictogen starts with a P. P-N-I-C-T-O-G-E-N. And then the chalcogens is the oxygen group, and halogens, and then noble gases. Now, these down here also have names. This is the lanthanide series, because it goes from left to right. It's not really a group. And it's named for the first member of its group, which is lanthanide. And then this is the actinides, and they're named for their first member, actinium. Notice these are pretty heavy elements. In fact, there's uranium right there, and there's plutonium. It's got that symbol the way it is because it's man-made. You don't find plutonium in nature. So when the U.S. government wanted to build well, actually their scientists wanted to build an atomic weapon using plutonium, they had to make it. Uranium, all they had to do was separate the isotopes to get the fissionable one. U-238 was the stable one, and U-235 was the unstable one. Only it's less than 0.5%. So it took a lot of work to get the 235 concentrated enough to make a weapon out of it. And that's what Iran's trying to do now. Okay, so those are the named groups. And notice this, the groups have this number attached to them, the Roman numeral. That's the old way of numbering the groups. From left to right, there's 1A, there's 2A, then you skip over here to the boron group, 3, 4, 5, 6, 7, and then sometimes they say 8A, sometimes they put a 0 up there. The value of that was, this one has one valence electron, one electron that's able to react with other elements. And what it usually does is it loses that electron. So that means every element in this group, when it forms an ion, it's always +1. So if you have sodium combined with chlorine, table salt, this one's going to be a +1 charge and that would be a -1 charge. And they're attracted by electrostatic force. This is an ionic compound because it's purely electrostatic. You form the ion, then they pull each other together. And this one always forms just like other members of its group. Lithium would be that way. Potassium would be that way. Rubidium would be that way. They all form +1. And that's the value of this 1A designation. The newer numbering system for the groups is just left to right. 1, 2, 3, 4, 5, all the way across to 18. And I think that was kind of a mistake. But IUPAC says, no, that's the way we're going to do it. The International Union of Pure and Applied Chemists, or a subgroup, a study group. decided that that's what they were going to do. They didn't like this other numbering system. In fact, if you've had any touched on chemistry in other courses, biological courses, anatomy and physiology, they'll mention the Octet Rule. Probably heard of that. This lends itself well to the Octet Rule. That Roman numeral 1, 2, 3, 4, 5, 6, 7, 8, at least for these two periods, it holds fast and true. In other words, the valence electrons, those that are in the outermost shell energy level of the atom, and this one is 1, this one is 2, this one's 3, this one's 4, 5, 6, 7, and that one has a complete outer shell. That's why they don't react with anybody. They don't want to give up electrons. They don't want to accept electrons. They're too noble. So we'll talk about that a little bit later. That's sort of a teaser. But when I had you fill out that extra credit, we used the newer system, just left to right, 1 through 18. But I just wanted to make the point that this is very useful. Now, when you get down in the transition elements, notice they call them Bs. In fact, this one doesn't even have a. That's because the Octet Rule doesn't hold for transition elements. And that will become obvious when we start talking about electronic structure of atoms. Why these don't follow the Octet Rule, while these do follow the Octet Rule. All right, we'll come back to that later. So here's well, that's a lot of detail to be crammed into a slide, and it's probably going to be hard to see in the video. But you notice this black line right here. That is the dividing line between non-metals and everybody else, metals. All right, not major division. We don't have the groups named, but no, we don't. We just identify groups and periods. Right? And the periods have numbers too. This first period has hydrogen and helium in it. That's it. And the only reason we put hydrogen over here above the alkali metals is just for balance. Hydrogen is an animal unto itself. It doesn't act like any of the other elements. So we really put it wherever we want to. And for balance, we put it over here, and then we put helium over here because it does behave like a noble gas. But we couldn't put hydrogen over here or here. We could have put it anywhere, actually. But we stuck it over there. Probably because most of the time when it forms an ion, it forms a +1 ion. But sometimes it can form a -1 ion. Well, it's kind of, well, hopefully when we start talking about compounds, I'll show you one. Let's just put it that way. Elements are arranged in the periodic table according to increasing atomic number. That's the way we do it now. Right? Originally, they were organized by increasing atomic mass. How are we doing? Am I eating up the time? Let's see. 11 o'clock, and then we have to go to lab. We'll see if we can finish. See if I can finish. Okay, so I mentioned metals earlier. Some of the characteristics of metals, right? They're lustrous, especially if you polish them. They're very good conductors of electricity and heat, electricity. They're malleable. I mentioned ductile also. You can stretch them into thin wires. Non-metals, on the other hand, oh, and did it say, no, it didn't say, most of them are solids. Whereas non-metals are just the opposite of metals. Right. Let's see, metals, non-metals. Oh, it doesn't even say. Well, they can be either solids, or this one I think is a gas. No. That's probably iodine. Iodine's a solid, but it's very volatile. So it'll sublimate. That is, it'll go directly from solid to gas, kind of like dry ice. Right? That's a common example of sublimation. Dry ice is solid carbon dioxide. So you take a piece of it and throw it out on the ground, it's like steaming. That's the carbon dioxide going straight from solid to gas. But these will occur in solids or liquids or gases, all three forms. They don't conduct electricity, they don't conduct heat very well. They're not shiny. They're brittle. Solids are brittle. Okay. Oh, there's our table. This came straight out of your textbook. Table 3. It just compares the metals and the non-metals based on physical properties. Right. So on this dividing line, we see that metals over here and non-metals over here, but there are a few that are really close to that dividing line. And some of them, depending on the circumstances, behave like metals, and sometimes they behave like non-metals, even if they're on the other side, one of the other side of that line. Those are called metalloids, like silicon and germanium, arsenic, antimony, tellurium. They have a tendency to behave differently depending on their environment. And it's actually good. I mean, we've got a multi-billion-dollar, it's probably trillion-dollar industry built around it. Electronics. They use silicon as the basis. Right? And they have pure silicon, and they dope it with elements either from this side or from this side of the silicon, and it produces semiconductors eventually. So the metalloids are economically very valuable. Okay, differences between metals and non-metals, all of those. Okay, now we're going to talk about the electronic structure of the atom. I know you've all been waiting for this. Chomping at the bit to draw an atom's structure. Now, why do we want to know the electronic structure of an atom? Well, as chemists, it helps us understand what happens during a chemical reaction, why chemical reactions occur, based upon where the electrons are in that space around the atom. I mean, they're just not floating out there. They're occupying regions of space, although, unfortunately, we don't know exactly where they are. We do know we can characterize their energies, which is actually more important than where they are. But we can say something about the region where they might be found. So once you get down to that level, that subatomic level, we're starting to talk in terms of probabilities. What's the probability of finding an electron in this region? And as it turns out, that's good enough. And it's all coalesced into a discipline called quantum mechanics. So, familiar with classical physics. When I think of classical physics, I think Isaac Newton. His first law, things in motion tend to remain in motion, or things at rest tend to remain at rest unless acted upon by an external force. That's a consequence of mass, inertia. Second law, if you apply a force to a mass, it will accelerate at a prescribed change in velocity. You can put that in this formula. Force equals mass times acceleration. That's his second law. His third law See, I paint myself into a corner. His third law is action-reaction. That's why rockets work. When one thing pushes against another, it pushes back with equal force. So if we're on ice, on skates, where there's a little friction, we push against each other, we both feel the force, equal force. And then he morphed that one into the Law of Universal Gravitation and gave us a formula for that also. So two bodies in space will attract one another with this force based upon the mass of one of them times the mass of the other one divided by the square of their distance. Oh, and then we had a proportionality constant. Right? So all of those are considered part of classical physics, classical mechanics. When you get really, really, really big, like black hole size or centers of galaxies, then those laws fall apart. And when you get to that point, you're talking about relativity. So that's when Einstein comes into play. But when you get really, really, really small, classical physics also falls apart. It can't explain it. So then you get quantum mechanics. That stepped in to explain the behavior of very small things. We're talking about electrons now. Okay. So you're not going to have to, I can't teach you how to do quantum mechanics. I can teach you some of the things that we learned from quantum mechanics, right? And help inform how we draw an atom and how we explain chemical behavior. That's what we're getting at here. All right, so think of an atom with its dense nucleus and the electrons out here, and the electrons are positioned based upon their energies. So the closer the electron is to the nucleus, the lower its energy. Think in terms, if the electron is attracted very strongly, of course it would be, to this positive center, this nucleus, then how are you going to get that electron to move further from the atom? You have to add energy to it to move it away from that strong attraction. So add energy to it, it moves further away. So the higher energy electrons are further away from the nucleus. And we can put them in shells. The electron shell is characterized by this number n. That's the principal quantum number. And it always explains energy. Now that's a general, it's like an energy region. But it's a number, it's a whole number between 2, 3, whole numbers, starting with 1. They have approximately the same energy if electrons have that number. Right. Well, we're going to describe 4 numbers. These are quantum numbers. The first one is energy. And they spend, when they have that number, they spend most of their time approximately in the same distance from the nucleus, this shell. Okay. Then within each shell, say we have a nucleus here. Let's do it here. So we have our nucleus here, and then we have shells here. 1, 2, 3, 4. So electrons that are in this region have a certain energy, and electrons in this one have more energy, more energy, more energy. But within each one of these shells, you have subshells. And we give that an L number. And this L refers to the angular momentum of the electrons that are within that energy shell. Okay, and the numbers we give it are, this is a subset of that. So we can have a subset of this one of that energy level. We can have a subset here of that energy level, of that energy level. So it's like it's got this energy level, and it can have these sublevels. But if you have this one over here, it can have its own sublevels. Right? It's kind of like an apartment building. You have different floors, and you have apartments on that floor. Right? That's your L's. But within the apartment, you have other different regions, like the kitchen, the bathroom, and so forth. So and they can just balloon, right? One apartment building, maybe it has 5 or 10 floors, but count up all the restrooms. Right? They can be massive numbers of restrooms. So we're branching with each level, right? We're going to have L's here. This is the angular momentum quantum number, and within this, if this is 1, we can have 0. With 2, we can have 0 and 1. With 3, we can have 0, 1, and 2. Right? So that's what we got here. Those sublevels. Okay. I know this is getting complicated, but just hang with me. These subshells, rather than identify the N and the L numbers for the electron as 1, 0, or 2, 0, 1, or 2, 1, or 3, 0, 3, 1, 3, 2, we give these sublevels letters. All the zeros in each one of these are S's. Okay. All the 1s are P's. All the 2s are D's. Okay, and the 3s would be F's. S, P, D, F. We can have G's also, but those first 4 are the ones we use most often. So here are the subshell letters. Okay. All right. This is not going to make any sense yet. So let's move to the next level. So inside each one of these sublevels here, you can have an M sub L. And the M sub L is the magnetic quantum number. Okay, so within each one of these, you can have minus L up to plus L. So 0, you can only have 1. Right? So this one can only have 1. This one can only have 1. This one can have minus 1, 0, plus 1. For this one. So 2 could have what? Minus 2, minus 1, 0, plus 1, plus 2. Got 5 levels. So the P's can have 3 M sub L's, and the D's can have 5 M sub L's. Let's see where it balloons. Okay, and within this one, the last level is M sub S, which is the spin quantum number. Think of electrons as rotating spheres of charge. Right? It can spin this way, or it can spin that way. So within each one of these, however many here, this one, any one of these 3, any one of these 5, you can either have minus 1/2 or plus 1/2. That's it. Okay, so now we can count up. Each one of these can have 1 electron in it. So you can have 2 electrons in each one of these levels. You can have 2 electrons in here, 2 electrons there, 2 electrons there, or minus 2, minus 1, 0, plus 1, plus 2. You can have 2 electrons here, 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 and here. Okay, so that's what that chart was on the previous one. For the s orbitals, you can only have 2 electrons. You only have 1 there. You can have 2 electrons here. That's it. You're full. That's why on this side, you've only got 2 groups. There's 1 s electron and there's another s electron. That's it. When you get over here, you've got the p's. Here, you can have 3. 3 m sub L's with 2 electrons each makes 6 electrons, right? And think of as we're adding electrons, it's because there are more protons. So each time you add an electron, there's another proton, which means a new element. So when we move from left to right, this is the first electron in the P's. 1, 2, 3, 4, 5, 6. That's why you only have 6 over there, 6 groups. And if you put the S's and P's together, how many do you have? 2 plus 6 is 8. 8 electrons. So when you move from left to right, 1, 2, S, S, P, 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 P. That's 8 electrons. Octet. That's the basis of the octet rule that you've seen in other courses. Okay, so with the D's, you can have 2 each here. So 2 times 5 is 10. That's why you have 10 here. And with the F's, which would be 3, you can have -3, -2, -1, 0, +1, +2, +3. That's 7. So they can have 14 electrons because it's 2 each. That's why you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 elements there. These are all filling F orbitals from left to right. These you only have 10. Right here. D's. 5 with 2 each means 10 electrons and 10 protons to go with them. So left to right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 electrons. So these are filling S orbitals. These are filling P orbitals. These are filling D orbitals. And these are filling F orbitals. That's how the chart is organized. That's why I said, if you know how the chart is organized, you can draw the electronic structure of any element in its ground state, neutral state. Okay? Let me leave that up there for now. Let's see. All right, that just repeats what I did here. S's can only have one subshell, can only have one orbital. 1 m sub L is what they're saying here. 1 m sub L. P's can have 3 m sub L's. D's can have 5. F's can have 7. And each one of those can have 2 electrons in it with opposite spins. Okay? That's just what we think they might look like. Remember, I said this is all probability, right? It's all a numbers game. So the s orbitals are believed to be spherical in shape. The p orbitals look like dumbbells. And these p's here would be like that in one direction, but notice there are 3 of them, 3 possibilities. Well, on the x-axis and the y-axis and the z-axis. So that means that m sub L actually says something about orientation. Right? The orientation of these orbitals is the m sub L, whereas the shape is the L. Right? So the P's have this shape, the D's have that shape, the F's have this shape. And then this says something about their orientation in space. Orientation is important because when 2 elements come together, if they're going to react, they react with electrons. They don't react with a nucleus. So knowing where the energy levels and where approximate locations of the electrons helps inform how they're going to react when if they come together and they don't match, then you're not going to have a reaction. Okay, so, well, that's what I was saying earlier about X, Y, and Z axes. This is the easiest one to understand because it's really simple, dumbbell shape, and you have 3 possible axes it can orient. The D's and the F's get a little squirrely, and you have to approach those mathematically. which we're not going to do. We mentioned spin. Okay, so that's this one. In other words, those electrons are located in one of these M sub L's. And in order to do that, they have to have opposite spins. If they've got the same spin, they will kick one of them out. They can't exist together in that close proximity without opposite spins. Okay. They occupy shells, subshells, and orbitals. Shells, these are the names that are given by your author. Shells, subshells, orbitals. Okay. Do you have any questions so far? You want to think about it some more? Okay. I don't blame you. Okay, so there are various, when we start to write the electronic configuration, that's what we call it, a shorthand notation for where the electrons sit in their relative energy levels, shells, subshells, and orbitals. We need some rules to go by. And these are rules that have developed over the decades, and they're useful and they've proven themselves correct. First one. This is a German word, Aufbau principle. And from what I can tell, it just means do it this way. This is the way it's done. This is the way it's done principle. How electrons are placed into orbitals as you build atoms from one to the next. As you add a proton, you add an electron, and you build these atoms based upon where they came from, theoretically. Not theoretically, conceptually. Right? We add electrons from left to right. We put an electron in that orbital, so you can't put any more in there, right? Unless you put it at opposite spin. Okay, so there you go. You got those two. And then the next one, you got to go to, instead of an s orbital, you got to move up to a p orbital. And you build them up energy levels. Low energy first. If they're filled, you got to move to the next level. So it's like, let's say everybody that wants it to move into the apartment building, first come, first serve. Right? First ones that come, it's everybody wants to be on the lowest possible floor, just in case there's a fire, you can get out quicker. So the ones who get there first occupy apartments on the ground floor. And then those that come in later, they have to move up to the next floor. And they just keep stacking them up. Now that doesn't account for those who like penthouses, but the analogy only goes so far. So the Aufbau principle says you fill them in order of increasing energy. So you can't put one in a higher energy orbital until you get the lower ones filled. The next one is Hund's rule. Electrons occupy orbitals and subshells. Such that each orbital acquires one electron before any orbital acquires a second electron. So, all right, example. Say you've got, you're filling a p orbital, but there are three possible orientations, right? So you could have, you've got room for three of them, like X, Y, and Z. Well, Hund's rule says, and I'm going to use single bar arrows for an electron and spin. So if it's like this, it spins one way. If it's like that, it spins the other way. Okay. So Hund's rule says that you can have two, well, we know that you can have two electrons in there with opposite spins. But Hund's rule says you can't put opposite spins together until you get the same spin in all the available orbitals. So we have to, as we move up number of electrons, say that element has one in this orbital. The next element, we put it in that one. we can't put it over here with this one. We got to go to the next one for the next highest number of electrons. Then you can start, as you're building element, 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 then you can start going back and do that. Hund's rule says that that's the order of operation. They have to be separate subshells, separate orbitals, actually. They have to be separated until you can go back and start filling them. I'm going to show you some examples, of course. And then Pauli exclusion principle. No two electrons, actually the way it's worded, no two electrons can have exactly the same group or numbers here. In other words, these sets of numbers are unique for every electron. So N would be 1. Well, the next electron, well, that can be 1 also. And you can have those two electrons can have the same numbers here. Or they could have the same numbers there, 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 there. But when you get down to here, they've got to have opposite spins. Or you could say electron in this N number and electron in that N number, and then work down. They all have to have unique sets of 4 quantum numbers. That's what Pauli exclusion principle says. You cannot have 2 electrons in the same atom with the same quantum numbers, exactly the same set. Right. Once I have that set of numbers, I'm an electron, nobody else can have it. Right. We're married. Okay. So as we're filling using the Aufbau principle, we're adding electrons in at higher and higher energies. We would normally think that 3 is higher energy than 2. And for the most part, it is. But when you get to 4, what you may find out is some of these subshells tend to switch energies. And this is all based upon calculations, probabilities. Well, and experimental data to back it up. What you find is that once you start getting more and more protons in the nucleus, more and more electrons interacting with one another in space, they tend to shift the order of energy. So here's an example. Once you get up into the higher levels, the 4s orbital is actually lower energy than the 3d. So the Aufbau principle says, well, we got to put electrons in this one before we can go to that one. But it's sort of counterintuitive, except it's based upon experimental evidence. And this 5s has to be filled before the 4d. So we need a method that will help us do that. And I'm going to show you. I wonder if it's already in here. Is it on the next slide? Probably is. Let me just see. Yeah, it's in there. It's the next slide. Okay, so here's the method we use to account for these shifting energy levels, the counterintuitive shifting. We would expect 5 to be a higher energy level than 4. So this one we would expect to be up here underneath the P. But no, it's not. So here's the practical approach. Don't pay attention to these diagonals yet. Just look at this. Okay, there's 1s. There's the principal quantum number, and there's the shell. The shell and the subshell. Right? That's why we use letters instead of numbers, because numbers, too many numbers can get confusing. So instead of putting a 1 or a 0 here, we put an S. And here we put a P instead of a 1. And here we put a D instead of a 2. So it's easier to tell them apart. So if we list them up here, this is the 1 energy level, this is the 2, and it can have an S or a P in it. Right? Now, S's in the first energy level, right? If the quantum number is 1, then the only possibility for the L is 0. Right? It's always 1 less. You can't go any higher. So that's why there's only an S in the 1. That's why if you look at hydrogen and helium, you got an electron goes into 1 with 1 spin, and then the second electron goes in with the opposite spin. That's where it resides. There's no other possibilities. Okay, for the 2, you have a 2s and a 2p. For the 3, you can have an sp and a d, based upon that rule. And the 4, you can have an sp, d, and f. 5 could go up to g. 6 can go even higher, but there are not enough elements up here to account for those orbitals. So those are mathematical curiosities, actually. In reality, you only need that number in that arrangement without going further out here to get all of the elements in the periodic table. All 118 of them will fit in that format. So once you've got them energy levels and subshells like this, then you draw your diagonals. So you draw a diagonal here, right? 1s, fill that one, then you go fill this one, then you go fill that one, and this one. So 1s, 2s, 2p, 3s. So far, everything's in order. And then 3p, that's in order. But instead of going to D, now you have to go down to 4s. And once it's filled, you come back up to 3d. And then you go down to 4p and 5s. And then you go back up here. So that gives you the order of filling. Fortunately, well, you can use that. But if you know how the periodic table is structured, you don't need that. Let's see, do I have another slide for that too? Let's see. I might have to do that one freehand. That works. Okay, but let's draw an electronic configuration. This is how electrons are going to fit into the atom. Energy levels, subshells, orbitals. As we get more and more protons and add electrons to neutralize them. And this is the way they're going to go. So let's look at nitrogen as an example. Okay, nitrogen has 7 electrons, 7 protons, and we're talking about neutral right now. 7 electrons. Okay, so how would it fill? Well, if we use that diagonal, the first one is the 1s. Right? So it has 2 electrons in it. We got 5 left over. So next we'll go to the 2s. And we got 5 electrons, use 2 of them, now we got 3. So next one we go to is 2p. We got 3 in the p's, like that. Now remember, the s's only have 1 orbital with 2 electrons each. But the p's can have 3, right? The m sub l's. So if we want to be more detailed, we would say those 3 electrons look like this. Okay. 1 upspin in each of the 3 subshells. Orbitals, I should say. Each of the 3 orbitals. But this shorthand is usually enough. Okay. There we go. That's known as condensed notation. Rather than having to draw out a graph with energy levels, this is more convenient. Right? And this, notice that this 3 p's, 1, 2, 3. We're filling p orbitals here. So that's 3 electrons in the p orbital. We fill the S1s orbital, and notice these periods, right? That's period 1, 1s. Period 2, 2s, 2p. Period 3, 3s, 3p. Okay. This one is 4s, and these are 4p. Remember our diagonals? When we start filling d orbitals, we've got to go back 4s, 3d. Because with n equals 1, you can have, you can only have s's. With 2, you can have s's and p's. With 3, you can have s's, p's, and d's. So when the first opportunity to fill d's is in the 3. We're on the 4th period, but these are 3d orbitals. 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you had a d there, it would have 5 of these. Instead of the p, which only had 3. And then you would just do like this, like this, like this, like this, like this, until you had 5. 1, 2, 3, 4, 5, and then you start back here, like that, until they were all filled up. Now, there are peculiarities and exceptions to the rule, but I'm not going to talk about those right now. They just muddy the water too much. Okay, so what's another example? Let's try another one. That's what nitrogen looks like. How about sulfur? Okay, we did nitrogen here. Now there's sulfur. Sulfur has 16, correct? 16 protons, 16 electrons. And this is going to be the same thing for any of the isotopes. Doesn't matter. Right? So let's use the periodic table to fill this up. 1s, 2 electrons. Right? 2s, 2 more electrons. How about 2p's? Well, 2p's, 1, 2, 3, 4, 5, 6. And then we go back down here to 3s. 3s, 2 electrons. And then we're down to 3p. We have 1, 2, 3, 4. 4 electrons. Okay, so that's 2, 4, 6, 12, 16. That accounts for all of our electrons. And all we had to do was just follow along, filling them up until we get to our target right here. Okay? So that's how knowing the structure of the periodic table allows you to do this with the least amount of pain. Let's see. Now, barium, notice where barium's located, right there. You have a long way to get to barium. So are we going to draw the whole thing for barium? We probably should the first time we do it. And then I'll show you a shortcut. Because ultimately, what you want to know is how many electrons are in this highest energy shell. It's farthest from the nucleus. And when 2 atoms come together, what are they going to see first? Not just electrons. They're going to see those outer electrons first. Those are the ones that will react, the valence electrons. So really all we want to know is what's going on way out here at the highest energy. And drawing the whole structure is not wasted effort, but it's a little more effort than you need to explain what's happening. So let's do it the long way first. Barium's 56. Okay, so we have 1s2, 2s2, 2p6. We go down 3s and 3p, 3s2, 3p6. Okay, then we come back around to 4s, 4s2, and then we go to 3d. We're going to fill all those up. 3d, 10. I have to wrap around. And now we're back to 4p. Remember, this is where we backtracked on that diagonal. And then we got 6 in this one. All right, so we're down to here, correct? Now we go to 5s, 2. What's this one? 4d. 4d. 10. Okay. So now we're 5s, 4d10, and now we're 5p. 5p, 6. Okay, here we are, 5p6. Now we're down to 6s. 6s2. That's barium. Let's count them up to be sure. 2, 4, 10, another 10, 20, 30, 40, 48, 54, plus 2 is 56. So all our electrons are counted for. Okay, these are known as valence electrons. The highest energy orbital with the same number, the same n quantum number, the principal quantum number. Those are valence electrons. These are the ones that react. That's why barium and all the members of its group prefer to lose 2 electrons and make a 2+ charge when they form ions. They're losing those 2 right there. So why would they do that? Well, everybody wants to look like a noble gas. It's like the movie stars or supermodels, right? If you want to look like them, you got to do something. You either got to take or give. In this case, they give. Gives up 2 electrons. Now what does it look like electronically? If we're that ion, it looks like, let's see, it's back up 2. Lose 1, lose another one. Now it looks like xenon. Electronically, it's not xenon, but it has the same electronic structure as xenon. And it's complete. All of these are completely full of electrons, as many as they can hold. That's when they're happiest. When their shells are all full. That's why noble gases don't play with anybody. They don't need to. They've got full orbitals. I don't need electrons. I'm not going to give any up. So noble gases, they tend to just keep to themselves. But everybody else tries to look like a noble gas. For instance, before I leave this, let's do the shorthand. So if everybody tries to look like a noble gas, and the electrons that are beyond the noble gas configuration are the ones that react, then why don't we use this as our basis? Right? Xenon, and then we move around over here. That's 6s. 6s2. The electronic configuration of barium looks like xenon as its core with the valence tacked on. Right? So that's the ultra shorthand. Right? That's the full thing. And this is our shorthand notation. Okay. I started off really complicated, and now I'm trying to simplify, make things move faster and easier. Okay, so let's look at, that's what barium did. The easiest way for it to look like a noble gas was to lose those electrons. What about the other side over here? Right. Let's say chlorine is 17. Chlorine, 17, right? So what would it be? Well, if we use our shorthand notation, we'd go back to neon. You got to go backwards, 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 and then wrap around. So the lowest, the highest noble gas that's close to chlorine was neon. If we use this shorthand notation, right? So what would it be? Neon would be 10 here. And then we'd say 3s2 and 3p, 5. Okay, 7 electrons. It needs 1 more to look like argon. If we add 1 electron to that, we can get to argon. Or we can take away 7 electrons and look like neon. Which one's easier? Add 1 electron. Okay. That's easier. Energy speaking, energy wise, just add 1 electron. If you add 1 electron, then your ion is 1 negative. You've added an electron. So you've got 17 protons, 17 electrons, but you add 1, now you have 18 electrons. If you added another electron here, now you're looking like argon. So that's the same electronic configuration as chlorine ion. Okay? That's why all the halogens prefer a -1 charge. Because to get to look like a noble gas, all you have to do is add 1 electron. Or if you're going to make an ion out of this group, you usually add 2 electrons, right? And that'll step it over, or oxygen will step over and look like neon. Sulfur will look like argon. Selenium will look like krypton. Just add 2 electrons. Okay. Let's see what else what other trouble we can get into. Electronic configuration of sodium. What do you think? Sodium's 11, right? So it'd be 1s2, 2s2, 2p6, 3s1. All right, let's see. 1, 2, 2. It's this one right here. Okay. We're getting good at this, aren't we? Practice, practice. Practice doing this. Okay. And to make a long story short, that's why Mendeleev observed, well, others also observed common behavior of groups, simply based upon the tendency to accept or give up electrons. Right? All of these group 1s, like alkali metals, they have a 1 electron in outermost s orbital. And if they give up that electron, they look like a noble gas. These are known as valence electrons. Okay, so I mentioned this earlier. S orbitals here, p orbitals there. Well, helium, it only has access to 1s, so it's also s. And these are d orbitals. And we're not mentioning the f orbitals down here. I don't think I'll spring that one on you.
Please don't.
It's a little bit too much. Okay, what are they calling distinguishing electron? The last electron added to the electronic configuration for an element when a subshell is filled in order of increasing energy. Distinguishing electron. The last electron causes an element's electron configuration to differ from that of an element immediately preceding it. Okay. Minor point. Right. If you go from sulfur to chlorine, the distinguishing electron is the one that fills the 2p. The last one to go into the 2p orbital is the distinguishing electron. It sets it apart from sulfur. That's all they're saying. There's nothing magic about it. Okay, columns in the periodic table, right, are groups. Elements in these groups have similar chemical properties because they contain the same number of outer shell valence electrons. That's kind of redundant. Valence electrons are always in the outer shell. Okay. We've talked about metals versus non-metals. We've given them names, their groups. I mentioned representative elements here and here. I don't know where they got that name, representative. What do they represent? Right. Represent the Octet Rule, maybe? All right. Elements in group 1 and 2, they're always s orbitals. That distinguishes them from others. All right, detective story. We've got 2 elements. One is a gas and the other is a solid. Each contain identical number of electrons in their outer shell. These elements are blank, and they contain blank and blank neutrons, respectively. Well, let's see. One's a gas and one's a solid. Let's see. Gas, solid. Each contain identical number of electrons in their outer shell. They have the same number of valence electrons. Number of valence electrons. Same. Okay. Which one could they be? Same number of valence electrons. If they have the same number of valence electrons, and we're no ions here. So that means they have to be in the same family. Have the same number of valence electrons, they've got to be in the same group, right? So which one? Well, fluorine and iodine, they're in the same group, right? So that could be nitrogen and sulfur. Nope, can't be that one. They're in 2 different groups. Okay. Oxygen and sulfur, that could be. And fluorine and iodine again. Okay, what about the other condition? Gas and solid. Well, fluorine's a gas and iodine's a solid. That's true. Oxygen's a gas, sulfur's a solid. Okay, so that's okay. How about they contain blank and blank neutrons? All right, how many neutrons does fluorine have? Well, let's see. I got to get closer. And the most common isotope probably has 10. That's true. Right. So that lets this one out. Fluorine does not have, it has a mass number of 19 as one of its isotopes. So that one's out. So we're using test-taking technique, process of elimination. So D's out and B's out. How about this one? 16 neutrons for oxygen. Nope, that's mass number. So this one's out. So we've eliminated. This has to be it. Iodine should have 74 neutrons. So iodine has 53 protons and most common ion is 127. 53, yeah, 127. So it's a detective treasure hunt to find the answer. Let's see, we want to mess with this one. I'm out of time. We need to do lab next. I'm gonna let that one go. Okay, let's take a break. Humans are visual creatures. That's probably a maxim. Everybody knows that. That's not to say that someone who is vision impaired can't function. It's just that we prefer visual input. And in fact, if you are vision impaired, research has shown that the neuroplasticity, which if you've had anatomy and physiology, they've introduced that topic, neuroplasticity will allow parts of your brain that are being unused to be co-opted for other senses. So if your vision impairment is not as a result of damage to the occipital lobes, then those lobes will be, that brain tissue can be reused and co-opted for other senses like smell and hearing. But back to the topic. So we're looking at graphing techniques because when we present data, in other words, you do an experiment, you gather information, and you want to publish it, what you're trying to do is to convince others of your position. Convince them that what you're saying is correct. And one way to do it is to present your data in such a way that they can take it in quickly and understand your concepts. So there are a whole host of graphing techniques that are available. So we can't, by any stretch of the imagination, cover them all here. We're going to focus on the Cartesian system. If you've had any math at all, you probably understand. Remember the Cartesian system. It's got 4 quadrants. This is the x-axis, or the abscissa, and this is the y-axis, or the ordinate. And you can position data points anywhere in that Cartesian system with 2 numbers. The first number will identify the distance on the x-axis, and the second number on the y-axis. And let's just mark it off in. If you say this is 1, 2, 3, 4, and this is 1, 2, 3, 4, 5, the y-axis, then if you go out 2 and up 3, that point is identified in that position relative to this system, with this as your origin, right? That's 0, 0. Now, everything in this quadrant is positive numbers, both x and y. But you can go over here with negative x's and positive y's, or negative x's and negative y's, or negative y's and positive x's. So you can put it anywhere. This semester, any of the graphing we're going to do is going to be largely positive, but it may have some negatives when you graph your data. So you have to consider that when you're setting up your graph on a blank sheet of graph paper. You need to make room for all your data. Good. We'll talk about that a little more in a minute. But let's scroll up and see if I'm covering all the. Okay. As far as an experimental scientist is concerned, when you plot your data, you usually plot it with the independent variables on the y-axis. The independent variables are the ones that you control. So if we want to measure the volume change of a gas, if we change the pressure on the gas, then we have changed the pressure. That means it will be on this axis, and it needs units of measure. So atmospheres is common. That's not going to be picked up over there, is it? Atmospheres is common. And then volume will be the dependent variable, the one that changes as a response to what you did. And it will be on the y-axis. So in this example, that would be volume, and it could be in liters. Right? So you have identified the axis and the units of measure that are used on that axis. Okay? And then any point here we can identify as, if I increase the volume, increase the pressure to 4 atmospheres, what's that going to do to the pressure, to the volume? Well, maybe it squeezes the gas down to only 1 liter, just as an example. Or if we let the pressure off to say 1 atmosphere, maybe the volume balloons up to 4 liters. Independent, dependent. We already named the axes and the quadrants. We've already done that. Let's see. That's the trouble with this clicker. It only goes page at a time. It doesn't scroll. I got my eyes on a scroller pointer. I said to find the money first. And it'll have a little trackball on it, and you can scroll up from a remote. It's kind of like a wireless mouse, only you hold it in one hand and you operate the. Has anybody ever used a trackball? It's kind of like a mouse, only it's got a ball in it that you rotate with your thumb, and you move your mouse just like that. Once you get used to it, it's pretty neat. You don't have to move your mouse all over the place. It just sits right there. You move the ball. Well, they got one of those for your hand with a laser built in. Okay, so in this case, we're plotting temperature versus volume. Now, usually when you put data up in a table, which is a valid way to present your data if it's a small data set. But if it's a huge data set, then graphing is a better option because you can get a lot of information on a graph in recognizable form. That would be just overwhelming if it were in a table. But this is a short table, and we're just going to graph it. So we're changing the temperature and watching the volume change. So which one is the independent and which one's the dependent? Temperature is the one we changed, right? And this is the response, change in volume. So when you plot it, and I've chopped off the x-axis, but use your imagination. There's an x-axis down here. And you follow along the x-axis until you find whatever that temperature is. And then you go up to the volume that it corresponds. And there's your point. You drop your point right there. Notice something else about this graph. And this is true of any graph that you create, especially one that you want to publish. Graphs need to stand on their own four legs, which means I could, as a reader, take that graph and rip the page out of the journal, take it with me. And I wouldn't need to have the descriptive, the narrative in the article to tell me how to read that graph. Everything I need is right there on the graph, either in the graph itself, in the title. This has an accompanying table. Sometimes that's done. And there may even be footnotes with superscripts located here and there to the footnotes for additional information. But that graph stands on its own. It can be extracted from the article and within limits, explain itself. So that's why at a very minimum, a graph will have the axes, the units on the axis, what those units represent, and it'll have a title that will describe what the graph is trying to explain. And then it'll have the points plotted. Sometimes, not always, but sometimes, there's a best fit line or a best fit curve placed over those points. And the way you draw the best fit line is to minimize the variation among all the points. So if it's a straight line, you try to make the line come as close to all of them as possible. Minimize the deviations. It's easier to do with a straight line than it is with a curve. But some computer programs will help you out if you're proficient with that. Excel does some curves. It's very, very rudimentary. There's another program called Sigmoid that I used to use a lot, and it would do a better matching of the curve. And also, it would also, when you were satisfied with the curve, it would spit out a formula for that curve. Anyway, so when you draw a best fit line that encompasses all of your data points, you can stop there. Or if there's something else you want to say about it, you may extend your line outside that data point set. That's called extrapolation. right? That's why these are dotted lines, because there are no data points up here to support that extension. You're saying that the line is good enough so that you believe that if you were to increase the temperature to this value, that you would be somewhere in that neighborhood with the volume. If you stay within the data points of your set, that's called interpolation. I don't have a point here, right here, but based upon that best fit line, I may be able to draw conclusions. Say, what temperature would I have to be to increase the volume to, say, 0.6 liters? And I would come over here to where the line crosses 0.6, and then I would drop straight down and find the temperature. That's interpolation. Okay. Well, there's the temperature scale. We'll talk a little bit more about this when we get to gases. We talked about temperature already, I'm sure. So, and I described how Kelvin was developed, did I not? Okay, that was an extrapolation. That was an extreme extrapolation by Lord Kelvin. That took the temperature line way out and dropped the volume to 0, which is impossible. But theoretically, he extrapolated that line all the way down to the baseline and came up with his new system of temperature measurement. Okay, let's see. Right, so there's reference to the straight line and smooth curve. Smooth curves are a little more difficult to draw. If you have access to a French curve, everybody remember or have ever seen a French curve? If you get a graphing set, it will always have a compass, with a needle on one side and a pencil lead on the other, and you can make it wider or narrower and draw a circle. Okay, compass. There's also or is that a protractor? It's a protractor. Compass is the one with degree marks on it, right? Okay. And they'll have those. It'll have a ruler, and sometimes it'll have what's called a French curve. It's a piece of plastic usually, and it goes like this. It's very tight radius here, and then it expands like that. Right, then it goes maybe down like this. That's a bad drawing, but you get the idea. So you have different radius curvatures all around that French curve. So you can just move it around until it matches your data points and draw a smoother line using it. Now this is all, of course, for manual production, manual graphing. And that's where we're starting. There are computer programs that will help you out a lot with this. But this is so that you have a basic understanding of what's involved in graphing itself. It's like, let's see, most of you are going to MLT.
Yeah.
Okay. I don't know if they're going to do this, but maybe that's why they sent you the chemistry. So you get some hands-on with the old way of doing analysis. Right. So then when you go into MLT, everything's automated. Almost everything. Right. Your instruments are set up to do certain type of analysis. The reagents that you put into the instrument are prepackaged. Right, so you don't make any mistakes in concentrations and making the instrument work correctly. And that's for certification purposes too. So when the regulators come around and give you a referee sample, say analyze this, then you spit out numbers that are close to what they expect. Otherwise, you lose your certification and they have to shut the lab down. And then periodically, of course, you run your own test samples just to be sure everything's working right. In fact, some instruments are so squirrely, you may want to run a test sample with every set that goes through. In research, we used to do that a lot with certain instruments. Okay, so let me get back on topic here. Okay, so when you've got a data set, and you're going to draw it, what do you need to consider before you actually start putting things on that graph paper? Well, you're going to have your data in a table, probably. Right, numbers here. These X's correspond to these Y's. So there are your data points. So how do you know how to arrange them on your graph paper? What are you looking for? Well, what are you trying to say here? Let's use our previous example. Say this is temperature. Well, you want to know what are the temperature units. And this is volume. You want to know what the volume units are, because that's going on your graph. Then what else? You want to know the range. What range are you covering here for that temperature? Right? Are you going from maybe 100 K here to 500 K, or whatever the range happens to be? And over here, the response, liters, maybe it's a tenth of a liter here, and up here it's 20 liters. So you need to know the range of your data, so that when you decide how to put it on your paper, you can maximize your graph on that paper. You don't want to, always think of this. When you're drawing a graph, you're trying to convince somebody of your position. You're trying to tell them that this data is real and this is what it says. That's the whole purpose for a graph. So you think ahead, and what's the reader going to think when they see your graph? That's, assume you can get it past the reviewers. Well, what if you had a sheet of paper like this, graph paper, right, with all the lines here, and you said, okay, here's my y-axis, here's my x-axis, and here are all my data points. What's that going to look like to a reader? It's going to look like that you just graduated from kindergarten. You want to use the entire length of the paper. Right, so you want your data points to be spread out like this. So that means you've got to consider the x-axis range here and the y-axis range here to maximize it. Okay, then that means your points will spread out over the entire graph. And you can see minor variations a lot easier. And it's also easier to draw a best fit curve when they're spread out. Okay, so you need to know the scale, the range, and the scale. Then you need to know something about the orientation. This is going to be based upon standard letter size graph paper. It can either be portrait or landscape, right? So which way would you want to do it if it were portrait? If the Y range was huge and the X range was small, right? Because it would be this way. But if it's the other way around, if the X range is large and the Y range is small, you turn it landscape. Okay? Then what do you need to think about? Once you've got your orientation and you know your range, you think about, how am I going to put these numbers on this graph paper make it the easiest on myself? You don't want to set up your scale so that you've got decimal numbers and you're trying to figure out, where do they go, right? I've got lines here like this, like this, like that, like that, like that. And I've got it marked off major units here. Let's see, one, do another one. Major units here. And then I've got minor tick marks here. Then I'd like, for most of my points, that I can identify them exactly on a line. That's easier to position. If I know one data point on the x-axis is here, then I go up the y-axis over here, and it's easier to position my point, rather than trying to read between the lines and then estimate where it's supposed to go. Sometimes it's unavoidable, but you want to minimize the chances of error, and that's one of the ways to do it. So you need your major units and the size of your minor units. Because you'll see on those graph papers, they've got heavy lines and light lines. That's what they're there for. Now, between the heavy lines on that graph paper, there are only 5 steps. If you're in the decimal system, it'd be nice if you put 10 steps as subunits. Right? Then it's just move it over a decimal place, and it's easier to find your position. So if that's the case, if this is a major, and then you go 1, 2, 3, 4, 5 here, and you got another major, then if you can find a way to identify, to designate this one as a unit, say, I don't know, 0.5, and this one's 0.6, then each one of these marks will be a tenth of that, or the 100th position. This will be 0.51, 0.52, 0.53, 0.5, all the way across 0.6. And then if you've got a decimal fraction on one of your values, it's easy to find out where to put it. Okay, that's another consideration. Then, when you're expanding to use all the space, say we've got a landscape, and you're trying to use all this space. Well, suppose if you set it up so that this every other major tick mark is like that, with tenths subdivisions. But if you do it that way, then your maximum value is going to be out here. That'll never work. So you've got to shrink it back to get everything on the page. That's another consideration. Make sure that all your data will fit on the page. So it's sort of a balancing act. Right? You're trying to get everything out here spread out as far as possible, make it easy on yourself to position, and make it easy on the reader to find, to interpolate. Right? If they're interested in data points that you don't have, then make it easy on them. If you can make it easy on the reader, you're more likely to convince them of your position. Okay. Let's see. Drawing the axes. Oh, I mentioned earlier, it's possible to have negative values. So consider those also. The range includes the negative values too. So Kelvin is a perfect example, right? When he was proposing his system, right, he used 2 quadrants here, the positive and the negative positive. And when he extrapolated, right, there's a line. When he extrapolated, he went into the negatives on the x-axis. So if you've got any value, say negative x's, then you want to give yourself room here. And the origin is 0, 0 is not going to be on the far left edge of your page. It's going to be moved over into the middle of the page, so you'll have room for the negatives. I know one of the graphs is going to do that. That's why I'm making the point of this. All right, let's see. When you're drawing your best fit curve and trying to minimize variations, if you can find a transparent ruler, it'll work a whole lot better, because then you can see data points that you would be covered up by the ruler, either on one side or the other. So a transparent one, like, not that one. I thought I had one with me. Probably fell out of my pocket. Do you know what they look like? Okay, so we're plotting data points. Usually want to use a sharp instrument, like a pencil with a nice point on it. That way, you want it to be dark enough and bold enough so that you can see the point, but not so big that it obscures other information. And if you're using a computer program, you can vary that. In fact, you can make data points look like circles and squares and stars, whatever you want. And if you got Excel and you want to play with some of these things on Excel, that's great. In fact, I have some students that take the data and they plot it in Excel, and then they combine, they print out that and staple it there. So instead of drawing it by hand, they let Excel do it for them, which is okay. Do it either way. Let's see. Still see shadows there from the previous drawing. All right. Interpolating, extrapolating, we talked about that. You can, there's also a section in there on transforming data. So, and they're using Boyle's law. I know we haven't talked about gases yet, but this will come up again. Boyle's law is pressure-volume relationship of gases. So if you plot Boyle's law, right, with pressure here, and we'll just say atmospheres, and volume here, we'll just say liters, be consistent, parentheses. Then when you plot, as the pressure increases, what's going to happen? The gas is going to shrink. You can best think of that as just taking a plunger in a cylinder and pushing it down. You're decreasing the volume, but you're doing it by changing the pressure. And if you plot that, you find that as the pressure increases, the volume decreases. And Boyle's law will look like this, a hyperbola. Okay? Now, you don't have to remember that right now. The point I'm making is you can transform that data into a straight line because scientists don't like curves if we can avoid them. So all you have to do to turn that into a straight line is keep the pressure the same, those values the same in that data set, right? Pressure, volume, transform all the volumes into their inverses. So if the units here are liters, what are the units here? Liters to the -1. That's the way we say inverse, the -1 power. So if this one were 10 liters, what would this be? 1/10, right? 1 divided by 10. And you just do that all the way down. Then you plot pressure against 1 over volume. So now we've got 1 over volume, the -1. When you plot those values, you get a straight line. Okay. So there's an example of that in there also. I think they do use pressure and volume. But the point I'm trying to make is they also ask you to interpolate. In other words, once you get plotted, they're going to say, all right, what volume would it be if the pressure were such and such? So it says, all right, go out here. There's your pressure reading. What was the volume? Well, if you use a straight line, then it's easy to go up here like that and then across like that. But what's that value with this plot? That value is 1 over V. So once you find that value, you've got to take the inverse to answer the question. Remember how you construct a graph in order to use it properly. That's the whole point of that, the message of this section. Okay, any questions about that? Okay, it's easy to forget that. Right? You say, okay, I went over here. You stick that value in the answer and it's wrong because that's not the volume. That's the inverse of the volume. All right, that works pretty good. I guess it'll work okay until we load it up with toner. Okay. So when you look at a graph and you see the general trend of the graph, notice that I had that one before like this. That's known as a direct proportion because as this one gets bigger, that one gets bigger. This one gets bigger, up here, keeps getting larger. That's a direct proportion. Whereas, and that's with the 1 over V data as example. But with the straight data, just the pressure and volume, where you have this, that's an inverse proportion. Because as the pressure gets greater, the volume gets less. Inverse, direct versus inverse. So, and what's unique about those, I mean, what's instructive about those is with this one, 1 over V, and with this one, that's V, and this 1 over V, the relationship, whether it's direct or inverse, is quantified in the slope of the line. The slope of the line, remember how to do the slope of a straight line in math class? Rise over run. Everybody remember that? Yeah. Okay. Rise over run. So that is the change in y divided by the change in x is the slope. So if that's a positive value, right, both are positive, increase, increase, then the line is going to slope this way. So if the slope is positive, that's a direct proportionality. But if it goes the other way, it's like this, then the rise is negative. As you're going this way, this one actually decreases, right? So the change is negative. It goes from a high number to a low number. And we always say the change, the delta, let's use y. The delta y is the final minus the initial value. If the initial value is higher than the final value, then you get a negative number. So the slopes on these type of lines are always negative. Negatives are inverse. Okay. All right. What else? Oh, curves. How do you do the slope of a curve? Okay. It changes, right? Well, the slope here is like that. The slope here is like that. The slope here is like that. Constantly changing. That's why we like straight lines. But there's a concept in calculus. Anybody here had calculus? All right. The concept in calculus is instantaneous slope. That is, the slope on this curve varies, so we can only determine the slope at any given point. So at this point, the slope of that line is the slope of the tangent to that line. Remember that, don't you? Okay. So back to the point, that's why we like straight lines, because that's one slope, that's it, you're done. But with a curve, you got multiple slopes. It just depends on where you make your measurement. All right, let's see what other trouble we can get into here. All right, so we talked about the slope, and that straight line can be described in generic terms, right? Everybody's seen this one before, right? Y equals mx plus b. So there's your independent variable. There's your dependent variable. There's the slope of the line, and there's the intercept on the y-axis. When this is 0, that's where it intersects the line, the y-axis. Okay. And you can describe a line with that. Any straight line is describable with that formula. So if we determine the slope of this line to be m, whatever it is, how do we find out what the y-intercept is? All you have to do is, now you know m, plug it in here, and then find any point on that line, plug in the value of x and y for that point, and solve it for b. And there you got your y-intercept. Okay. I'll just use this. Okay. I think there's at least one example in there of writing the straight line formula. in those terms. Y equals mx plus b. Okay, let's see. This talks about units of measure. If you got change in volume divided by change in pressure, that will give you the slope of the line for, well, actually, this must be inverse data. That's inverse data. Volume is inverse here. So the units of measure in your slope are going to be liters to the -1, which is the inverse of our volume, divided by atmospheres, which means since it's in the denominator, we bring it up here in the numerator, now it's -1 too. So it's liters -1, atmospheres -1 as units of measure on the slope of that line. Okay, nonlinear relationships. Okay, what we mean by that is the curve doesn't behave, right? It could either be multiple curves or it could be a broken curve. And I think the example they use is a titration curve. In other words, you take some acid of a known volume and you add a little base to it. You measure the pH. Everybody know what pH is? I mean, we haven't talked about it yet, but it's a measure of acidity. Fresh marker. So I think the example, let's see if they're going to do that. Now, this is the pressure volume one. We talked about that one already. That's another example of nonlinear. Okay, here we go. Titration curve. And I'm not going to get it all on the screen, I guess, unless I change the scale. Now let me change the scale. Let's try 200, see if that gets it in here. Not quite. How about 180? Keep guessing. 150. That's good. So here we've titrated, which means you have a known amount of acid. In this case, titrations run the gamut, but we're specifying this is an acid-base titration. So you've got a certain amount of acid, and then you add base to it incrementally, a little bit at a time, and each time you add some, you measure the pH. So the independent variable is the amount of added base. That's what we're doing to it. So it goes on this axis. And we're measuring it in milliliters. Total amount of base added. And then what's the pH of that? That's the independent variable, dependent variable. Dependent variable is pH, right here. Okay, so what happens? Well, initially, the pH doesn't change very much as we add more and more base. Then it starts to go skyrocket. And at this point, we add just a little tiny amount of base and look at the jump in pH. And then it keeps going. We add a little bit more base. And then when it gets to this point, it kind of flattens out. That's also known as a sigmoid curve. Sigmoid from S. Right? S looks like this. But kind of lay it on its side. Yeah. That example. It's called sigmoid. Looks sort of like an S. Yeah. A stylized S. You'll see sigmoid curves lots of places. My bachelor's degree is in biology. We study sigmoid curves all over the place. They usually reference growth curves for populations. So population will start off very slow, increasing over time. It'll increase its size, and then it'll reach a point where it'll just explode like that. And you'll get huge populations very quickly. And what happens? They consume all their natural resources. So their population growth has to stop. Right? So you see that in nature all the time. This is a chemical example of a sigmoid curve. And it's nonlinear. In other words, the slope here is positive, but it changes rapidly here. And the slope here is almost vertical. And then it shallows out again, right? It's always positive, but it changes. And in calculus terms, this is known as the inflection point. Right? This is concave up, and this is concave down. And the point where those two swap is the inflection point. And in chemistry, that's also the equivalence point. That is where the amount of acid is exactly equal to the amount of base. All right, so you can draw your curve like that. It's difficult to fit a best fit line for something like this, because it's got so many different curves. You would have to use that French curve in multiple locations and draw parts of a curve to get it to work. All right. This is a broken curve. This is where we mix two chemicals together and we measure the temperature over time. And it increases very slowly in the beginning, and then all of a sudden it just goes like this. It goes from here to there over time. And then it settles down and starts to decrease again. So the best way to approach this one, if you want to know the difference in temperature between this part of the reaction and this part of the reaction, you draw a best fit curve here just for that section. And then you draw a best fit curve here for this section. And then you go back and you say, all right, where is this one maximized? Right in this region. And then you go up here and say, stay on this time right here. Don't deviate, go straight up on that time until it intersects the extrapolation of that line. Right? There's an example of that in here also. That's extra credit. So you don't have to tackle it if you don't want to. If you get the basics of drawing a curve, creating a graph, drawing a straight line, converting the pressure volume data into straight line data and drawing that, and then calculating the line, the slope, and giving the formula for a line, that'll be enough. Oh, and then using that straight line formula to predict an interpolated answer. I think that's all that's in the required section. And then this other stuff like the titration and this broken curve, I sectioned that off into extra credit bonus section. Okay. Okay, well, there are the other questions. Let's see. These only have 1 point to them because they're basically just regurgitating information. The ones that have a little more points on them, they require some thinking. Yeah, some of those are 1 point also. Let's see. And then we get to, so there's your graph paper, more graph paper, more graph paper. Yeah, did I skip over? Come on. Yeah, this is extra credit. I must have, there it is. Bonus. I flipped past it. So everything below that is bonus. Everything above that is the required section, which means if you work answer any of the bonus questions and get them right, then those points go into the calculation and the right answers are divided by the total required points. Right? So if you have a possibility of say 60 points in the total required, but you work some bonus and you get maybe 72 points, then you get more than 100%. That's the way I do the calculation. It doesn't cost you anything to try it. But don't forget, one of the biggest mistakes that my students make is when you draw a graph, be sure that it stands on its own 4 legs. all those indicators, like title, subdivisions of your line, of your axes, label the axes, what are the units, what do they represent, and then put your points in there. And then if the problem requires a best fit curve, put that in there too. So all those points, that's what I'm looking for. Right? If you forget to put a title, then you lose points. I want the graph to stand on its own within reason. Those basic bits of information need to be there. Okay, have we covered everything? I think so. Any questions? Besides, why do I have to do this?